Hello, nice to meet you. I am Dongjun Koo from the Translational Nanobioscience Research Center at Sungkyunkwan University. My topic for the presentation is biophysical characterization of LTX-315 anti-cancer peptide interaction with model membrane platforms. These days, cancer treatment strategies are transitioning to immunotherapies. Because of its limitations of conventional treatment, such as low selectivity, high cost, side effect, and multi-drug resistant issues. Among the various targeting agents, anti-cancer peptide, also known as ACPs, have recently emerged as one of the most promising classes of agents due to their high selectivity for cancer cells, low risk of drug resistance, and the ability to be chemically modified to improve targeting. And LTX-315 is a clinical stage promising anti-cancer peptide that is known to disrupt cancer cell membranes. The earlier studies shown that the LTX-315 peptide can directly permeabilize the plasma membrane of cancer cells to cause tumor necrosis while also interfering with mitochondrial membranes and inducing the release of danger-associated molecular pattern known as DAMP. Molecules that results in the immune cell homing to the tumor region. Damp release from permeabilized cancer cell can trigger immunogenic cell death, which is the way in which ACPs such as LTX-315 boost anti-tumor immunity through various mechanisms. What is interesting is that while membrane peptide interactions are the principal driver of the LTX-315 peptide's mechanism of action, there is still a lack of study on directly characterizing the membrane disruptive properties of the LTX-315 peptide, especially the studies using biophysical measurement strategies, which are already done in other antimicrobial and antiviral peptides are missing. So in here, we use the biophysical measurement strategies based on the cell membrane mimicking model membrane platform and surface-sensitive measurement approaches to characterize the membrane disruptive properties of the LTX-315 peptide. To track the membrane peptide interaction, we use three types of model membrane platforms: supported lipid bilayer, intact vesicle, and tethered lipid bilayer membranes with different membrane surface charges. Measurements were conducted using the quartz crystal microbalance dissipation, called QCMD, and the electrochemical impedance spectroscopy, the EIS techniques. So altogether, the two main parameters we test were the membrane surface charge and nanoarchitecture, and as a result, we have first figured out that in general LTX-315 preferentially disrupts negatively charged membranes and demonstrate enhanced attachment to curved membranes over the planar membranes. Thank you for listening.